Hello, this is Dr. Handel welcoming you to another unit in the Gold video series for Exam P produced by ACTEX. Today we are covering Module D2.8, the Poisson Distribution, in Category D2, Key Distribution Characteristics. We begin by discussing problem resources. Throughout these slides on distributions, illustrative problems are given. They are taken from the SOA sample probability problems. Candidates are encouraged to study these problems. Many of them are more challenging than the problems you find in textbooks. The URLs for the SOA probability exam sample problems and solutions are listed on the slides. The Poisson distribution is a very popular source of problems. The problems with the Poisson distribution are found at the following questions: 148, 164, 173, 212, 252, 267, 278, 289, 290, and 326. We begin with a standard illustrative example, question number 173. In a given region, the number of tornadoes in a one-week period is modeled by a Poisson distribution with mean 2. The number of tornadoes in different weeks are mutually independent. Calculate the probability that fewer than 4 tornadoes occur in a 3-week period. How do we solve this problem? How do we recognize that it's a Poisson distribution? First, the keyword Poisson indicates a distribution. Next, you need the parameters of the distribution. You are given a mean or average. In this case, 2 tornadoes per single week. Notice how averages require both a number, 2, and a period per week. You are asked to calculate a probability, in this case, fewer than 4, which means exactly 0 tornadoes, exactly 1 tornado, exactly 2 tornadoes, or exactly 3 tornadoes. Notice that the period may change. The period for the mean in the question is 1 week, 2 per week. The question for the probability is per 3 weeks. We first discuss basic facts and statistics about the Poisson distribution. The Poisson has one parameter, lambda. The average, mu, equals lambda. In our problem, that is 2. Variance equals lambda. In our problem, 2. The second moment, the variant of x, is the expectation of x squared minus the expectation squared. That means that lambda, the variance, is the expectation of x squared minus lambda squared, so the expectation of x squared is lambda plus lambda squared. The probability that the random variable x equal little x is lambda to the x over x factorial times e to the minus lambda. Sums of Poisson variables. Sums of independent Poisson variables are themselves a Poisson variable. Let's be more specific. Suppose we have n independent Poisson random variables, x1 through xn, with Poisson parameters lambda 1 through lambda n. Then x, which is the sum of x1 through xn, is also a Poisson random variable, with Poisson parameter lambda equal the sum of the lambda I. The symbolic statement is that if xi is distributed as Poisson of lambda I for I equal 1 through n, then Poisson of the sum of xi is distributed with parameter lambda equals some lambda I, and it's Poisson also. Using these facts, let's go back and solve the standard illustrative example. How do we deal with the transition from average per week to average per 3 weeks? Let x1 be the Poisson random variable for the first week in a 3-week period, so it has Poisson parameter lambda 1 equal 2. Similarly, let x2 and x3 be the Poisson random variable for the second and third week in a 3-week period. They have Poisson parameters lambda 2 equal 2, lambda 3 equal 2. Let x be the Poisson random variable for the tornadoes in a 3-week period. We used the formula on the last slide, sums of Poisson variables. X equal x1 plus x2 plus x3. In other words, the number of tornadoes in 3 weeks is the sum of the tornadoes in the first week, the second week, and third week. And it has Poisson parameter lambda 1 plus lambda 2 plus lambda 3, or 6. So x is the Poisson random variable number of tornadoes per 3 weeks, with Poisson parameter lambda equals 6. On average, you'll have 6 tornadoes every 3 weeks. We now use the probability formula on the basic stats slide. What's the probability of 0 tornadoes in a 3-week period? That's the probability x equals 0, so it's 6 to the 0 over 0 factorial e to the minus 6, which of course equals e to the minus 6. I can similarly compute the probability of exactly 1 tornado in a 3-week period, probability of 2 tornadoes in a 3-week period, or the probability of 3 tornadoes in a 3-week period. Let's just look at that. The probability that x equals 3 is equal to 6 cubed over 3 factorial times e to the minus 6, so it's equal to 36 e to the minus 6. So the probability of fewer than 4 tornadoes in a 3-week period is the sum of the probability of 0, 1, 2, or 3 tornadoes, or 61 times e to the minus 6, or 15.1%. We now deal with relation with other distribution. The Poisson distribution relates to several other distributions. A binomial distribution problem may be replaced by an equivalent Poisson problem. An exponential distribution problem may be complemented by an equivalent Poisson problem. Let's look at Poisson and binomial. A binomial distribution has 2 parameters, the number of experiments or trials, n, and the probability of success in each trial or experiment, p. The terms success and experiment are technical. You should review the binomial distribution model for further understanding. Here's the rule. If n is big and p is small, and lambda equal n times p, representing the average number of occurrences, is moderate, then the binomial problem with parameters n and p may be replaced with an equivalent Poisson problem with lambda. In symbols, bin n comma p is distributed approximately as Poisson lambda equals np. Okay, let's look at a sample problem where this can help us. Illustrative problem 252. The original question is as follows. A life insurance company has found there's a 3% probability that a randomly selected application contains an error. Assume applications are mutually independent in this respect. In order to randomly select 100 applications, calculate the probability that 95% or less of the selected applications are error-free. We would like to convert this question, which uses the binomial distribution, into a question using the Poisson distribution. The criteria for binomial Poisson conversion is as follows. N equals 100, that's rather large. P equals 3%, that's not as small. Lambda equal NP equal 3, which is the expected number of errors to be found, is a moderate value. Binomial Poisson conversion passes. Here is the converted problem. A life insurance company has found, on average, 3 errors for every 100 applications. Calculate the probability that 95% or less of the selected applications are error-free. Alternatively, calculate the probability that 5% or more of the selected applications have errors. The solution can now be done very simply. The probability that x, the number of errors, is greater than or equal to 5 is 1 minus the probability that x is less than or equal to 4, which is 1 minus the probability of exactly 0, 1, 2, 3, or 4. This can be calculated using the exact probability formulas, which is 1 minus e to the minus 3 times 3 0 over 0 factorial plus 3 to the 1 over 1 factorial plus 3 squared over 2 factorial plus 3 cubed over 3 factorial plus 3 to the 4th over 3 factorial, and that's 18.47%. Poisson and an exponential. Here's the rule. If an exponential distribution has a mean of mu, which is interpreted to mean that on average one waits mu units of time to the next event, then the problem may be reformulated as a Poisson distribution with mean lambda equal 1 over mu. That's interpreted to mean that on average 1 over mu events happen per unit of time. The symbolic statement is that the exponential with mean mu is distributed as Poisson with mean lambda equal 1 over u. Let's look at an illustrative problem illustrating the Poisson exponential relationship. We look at problem number 267. The original problem is the time until the next car accident for a particular driver is exponentially distributed with a mean of 200 days. Calculate the probability that the driver has no accidents in the next 365 days, but then has at least one accident in the 365-day period that follows his initial 365-day period. The conversion? Well, the exponential is a mean waiting time of 200 days out of 365 days, or 0.5479 per year. That's how much of a year you have to wait on average for the next accident. Then the Poisson mean occurrence per year is 1 divided by 0.5479 or 1.825 occurrences of accidents per year. The converted question states for a particular driver, accidents per year are Poisson distributed with a mean of 1.825 accidents per year. Calculate the probability that the driver has no accidents in the next 365 days, but then has at least one accident in the 365-day period that follows his initial 365-day period. Assume accidents in each year are independent. The Poisson solution is really very simple. The probability that x equals 0 is no accidents in the first year. The probability that x is greater than or equal to 1 states there is some accident in the next year, and that's equal to 1 minus the probability that x is less than or equal to 0. So the total probability is the probability that x equals 0 times 1 minus the probability that x equals 0. It's e to the minus 1.825 times 1 minus e to the minus 1.825, or 13.52%. The candidate is encouraged to test their mastery of the Poisson distribution by examining the SOA problems listed in the first slide. We particularly draw attention to problem number 326. This reviews the calculation of variance for a probability mixture. You should be thoroughly familiar with that. Problem number 148, this reviews the conditional variance formula, which is an advanced topic but is sometimes asked. Good luck in your exams.